Hey there guys, Paul here from theengineeringmindset.com. In this video, we're going to be learning how to calculate the cooling load for a cold room storage unit. Coming up, we'll look at what is a cold room and what are the sources of heat that we need to remove. Then we'll calculate a worked example with a safety factor, and we'll finish up sizing the refrigeration unit to suit this cooling load. Before we dive in, I just want to thank our partners over at Danfoss for sponsoring this video. They have an extensive collection of solutions for cold rooms that can help you meet future refrigerant and energy regulations without compromising on performance. Their free Cool Selector tool will also help you put these principles I'm sharing today into practice. You can download it for free at coolselector.danfoss.com. So first of all, what is a cold room and how does it work? A cold room is used to store perishable goods such as meat and vegetables to slow down their deterioration and preserve them as fresh as possible for as long as possible. Heat accelerates their deterioration, so we need to cool down the food by removing the heat. And to remove the heat, we use a refrigeration system, as this allows us to accurately and automatically control the temperature to preserve the goods for as long as possible. So where does the heat come from that we need to remove? Well, typically 5 to 15% is through transmission loads. This is the thermal energy transferred through the roof, the walls and the floor into the cold room. Now, heat always flows from hot to cold, and the interior of the cold room is obviously a lot colder than its surroundings. So heat is always trying to enter the space because of that temperature difference. If the cold store is exposed to direct sunlight, then the heat transfer will be higher, so an additional correction will need to be applied to allow for this. Then we have product loads, which account for typically 55 to 75% of the cooling load. This accounts for the heat that is introduced into the cold room when new products enter. It's also the energy required to cool, freeze and further cool after freezing. If you're just cooling the products, then you only need to consider the sensible heat load. But if you're freezing, then you need to account for the latent heat also as a phase change occurs. So there is energy used, but you will not see a temperature change while the product changes between a state of liquid and ice. Then there is an additional energy required to further chill this food down below the freezing point, which is again a sensible heat load. You also need to account for the packaging, as this will inherently be cooled also. Lastly, if you're cooling fruit and vegetables, then these products are alive and they will generate some heat, so you need to account for the removal of this also. The next thing to consider is the internal loads, which account for around 10 to 20%. Now this is the heat given off by people working in the cold room, as well as the lighting and equipment such as forklift trucks, etc. So for this, you'll need to consider what equipment will be used by the staff members in order to move the products in and out of the store, how much heat will they generate, and how long will they and the equipment be in the store for per day. Then we need to consider the refrigeration equipment in the room, which will account for around 1 to 10% of the total cooling load. For this, we want to know the rating of the fan motors and estimate how long they will run for each day. Then we want to also account for any heat transferred into the space due to defrosting the evaporator. The last thing we need to consider is air infiltration, which again adds around 1 to 10% to the cooling load. This occurs when the doors open, and so there is a transfer of heat into the space through the air. The other consideration is ventilation. Fruit and vegetables give off carbon dioxide, so some stores will require a ventilation fan. This air needs to be cooled down, so you must account for this also if it's used. So let's now run a simplified example of a cooling load calculation. Now, if you're doing this for a real world example, then I recommend you use a design software such as the Danfoss Cool Selector app for speed and accuracy. First of all, let's start with the transmission load. The dimensions of our cold store are 6 meters long, 5 meters wide and 4 meters high. The ambient air is 30 degrees Celsius at 50% relative humidity, and the internal air is 1 degree Celsius at 95 degrees relative humidity. The walls, roof and floor are all insulated with 80 millimeters of polyurethane with a U value of 0.28 watts per meter squared per Kelvin, and the ground temperature is 10 degrees Celsius. Now just to note that the manufacturer should tell you what the U value is for the insulation panels. If not, then you will need to calculate this. To calculate the transmission load, we'll be using the formula Q equals U multiplied by A multiplied by the temperature out minus the temperature in, multiplied by 24 and then divided by 1000. The U value we already know. A is just the surface area for the walls, the roof and the floor, and we'll calculate that in just a second. The temperature in and temperature out we already know. 24 is just how many hours there are in a day, and we divide by 1000, as this formula will calculate the value in watts, but we want to know the answer in kilowatts, so we just divide it by 1000. To calculate the area, A, is fairly easy. It's just the size of each of the internal walls. So drop the numbers in to find the area for each wall, the roof, as well as the floor. Then we can run these numbers in the formula that we saw earlier. You'll need to calculate the floor separately from the walls and the roof, as the temperature difference is different under the floor, so the heat transfer will therefore also be different. If the floor isn't insulated, then you will need to use a different formula based on empirical data. We can combine the walls and the roof to see that the daily heat gain is 22 kilowatt hours per day, and then we can also calculate the floor to be 1.8 kilowatt hours per day. Therefore, the total transmission cooling load is 23.8 kilowatt hours per day. Now remember, if your cold room is in direct sunlight, then you'll need to account for the sun's energy also. Next, we will calculate the cooling load from the product exchange, that being the heat brought into the cold room from new products entering which are at a higher temperature. For this example, we'll be storing apples. Now you can look up the specific heat capacity of the apples, but do remember, if you're freezing products, then the products will have a different specific heat when cooling, and then for freezing, and then for subcooling. So you'll need to account for this also. But in this example, we're just cooling apples. There are 4,000 kilograms of new apples arriving each day at a temperature of 5 degrees Celsius, and the store maintains a hold of 20,000 kilograms of apples. We can then use the formula Q equals M multiplied by CP multiplied by the temp enter minus temp store divided by 3,600, where Q equals kilowatt hours per day, M equals the mass of new products each day, temp enter is the entering temperature of the products, temp store is the temperature within the store, and 3,600 is simply to convert kilojoules to kilowatt hours. We can then drop the numbers in and see that it equates to 16 kilowatt hours per day. Next, we calculate the product respiration. Now this is the heat generated by living products such as fruit and vegetables. These will all generate heat as they are still alive. That's why we're cooling them down to slow down their deterioration and preserve them for longer. For this example, I've used 1.9 kilojoules per kilogram per day as an average, but this rate changes over time and with temperature. Now you can use rules of thumb such as this one just to simplify the calculation, but the precision of your answer will reflect how critical the cooling load needs to be. To calculate this, we'll use the formula Q equals M multiplied by resp divided by 3,600, where Q equals kilowatt hours per day, M equals the mass of products in storage, resp equals the respiration heat of the product, and 3,600 is just to convert the kilojoules to kilowatt hours. If we drop those numbers in, then we'll see it comes out at 10.5 kilowatt hours per day. For the product section, we'll just sum the exchange and the respiration load together to get 26.5 kilowatt hours per day. Next, we'll calculate the internal load from people working in the cold room, as people generate heat and we need to account for this. We'll estimate 2 people working in the store for 4 hours a day, and we can look up to see that at this temperature they will give off around 270 watts of heat per hour that they're inside. For this, we'll use the formula Q equals people multiplied by time multiplied by heat divided by 1000, where Q equals kilowatt hours per day, people equals how many people who are inside, time equals the length of time they spend inside each day, and heat equals the heat loss per person per hour. 1000 is just to convert the watts to kilowatts. So dropping those numbers in, we should see that we get 2.16 kilowatt hours per day. Then we can calculate the heat generated by the lighting. Now this is fairly simple to do, and we can use the formula Q equals lamps multiplied by time multiplied by wattage divided by 1000, where Q equals kilowatt hours per day, lamps equals the number of lamps, time equals the hours of use per day, wattage is the power rating of the lamps, and 1000 is to convert the watts to kilowatts. So if we have 3 lamps inside at 100 watts each, and they run for 4 hours a day, then we should see that these would give off around 1.2 kilowatt hours of heat per day. For the total internal load, we then just sum the people and lighting load together to get the value of 3.36 kilowatt hours per day. Now we can calculate the heat generation of the fan motors in the evaporator. In this cold room evaporator, we'll be using 3 fans rated at 200 watts each, and we'll estimate that they will be running for 14 hours per day. We can use the formula Q equals fans multiplied by time multiplied by wattage divided by 1000, where Q equals kilowatt hours per day, fans equals the number of fans within the evaporator unit, time equals the daily run hours, wattage equals the rated power of the fan motors, and 1000 is to simply convert from watts to kilowatts. So if we drop these numbers in, we'll see that the answer comes out at 8.4 kilowatt hours per day. Now we will calculate the heat load caused by the defrosting of the evaporator. In this example, our cold room uses an electric heating element rated at 1.2 kilowatts. It runs for 30 minutes 3 times a day, and the transfer efficiency is 30%. So 30% of all the energy it consumes is actually just transferred into the cold room. We will then use the formula power multiplied by time multiplied by cycles multiplied by efficiency, where Q equals kilowatt hours per day, power equals the power rating of the heating element, time equals the defrost runtime, cycles is how many times per day will the defrost cycle occur, and the efficiency is which percent of the heat will be transferred into the space. So if we drop those numbers in, we'll see that the value comes out at 0.54 kilowatt hours per day. The total equipment load is then the fan heat load plus the defrost heat load, which is 8.94 kilowatt hours per day. Now we need to calculate the heat load from air infiltration. I'm going to use a simplified equation, but depending on how critical your calculation is, then you may need to use other more comprehensive formulas to achieve greater precision. We'll estimate that there will be 5 volume air changes per day due to the door being open. The volume is calculated at 120 cubic meters. Each cubic meter of air provides around 2 kilojoules of heat per degree Celsius of temperature difference, and the outside air is 30 degrees Celsius, whereas the inside air is 1 degree Celsius. We can then use the formula Q equals changes multiplied by volume multiplied by energy multiplied by temp out minus temp in divided by 3600, where Q equals the kilowatt hours per day, changes equals the number of volume changes per day, volume equals the volume of the cold store, energy equals the energy per cubic meter per degree Celsius, temp out is the outside air temperature, and temp in is the inside air temperature, and 3600 is just to convert from kilojoules to kilowatt hours. So we'll drop those numbers in and we'll see that that comes out to 9.67 kilowatt hours per day. Now we need to calculate the total cooling load, so for that we'll just need to sum up the calculations that we've just performed, and we'll see that that comes out to 72.27 kilowatt hours per day. We should also then apply a safety factor to the calculation to account for errors and variations from design. It's typical to add 10 to 30% onto the calculation to cover this. I've gone with 20%, so we'll just multiply the cooling load by a safety factor of 1.2 to give us our total cooling load of 86.7 kilowatt hours per day. The last thing we need to do is calculate the refrigeration capacity to handle this load. A common approach is to average the total daily cooling load by the runtime of the refrigeration unit. For this, I'm estimating the unit to run 14 hours per day, which is fairly typical for this size and type of store. Therefore, our total cooling load of 86.7 kilowatt hours per day divided by our 14 hours of runtime means that the refrigeration unit needs to have a capacity of 6.2 kilowatts to sufficiently meet our cooling load. Okay, that's it for this video. Before we wrap things up though, I just want to thank Danfoss one last time and remind you to give everything you learned today a try by downloading their free Cool Selector tool at coolselector.danfoss.com. Thanks for watching. I hope you've enjoyed this and it's helped you. If so, then please like, subscribe and share, and leave your comments and questions below. Also, don't forget to follow us on Facebook, Twitter and Instagram, and check out our website, theengineeringmindset.com.